Let's learn about electron energy levels and quantum numbers. Hey guys, welcome back to Monroe Tutoring. And if it's your first time, just welcome. Let's jump right in. And if you guys remember my lecture on subatomic particles, I mentioned that the protons and neutrons exist at the core and the nucleus of an atom, and that the electrons whiz around on the exterior. Now, sometimes we use the analogy that the electrons go around the nucleus, kind of like the planets go around the sun. And it's a useful analogy, kind of like how there's planets that are closer to the sun, planets that are further than the sun, or from the sun rather, and that these correspond to different energy levels. It's useful for visualizing, but it's not really a true representation of how an atom really works. So instead of the electrons going around the nucleus in orbits, like the planets do with the sun, they go around in what we call orbitals. And an orbital is a three-dimensional space where you're most likely to encounter an electron, okay? So electrons exist as like a probability, and we have a wave function that defines that, and we can look at like a density map in 3D space of where an electron is most likely to be in relation to its nucleus. That's not too important for this. That's getting it a little into quantum mechanics. Now, let's just keep it simple here for Gen Chem and talk about what you guys really need to know. But the idea is that electrons exist in these clouds of where they could be, and different energy levels and different orientations have different shapes. So now let's get into the bulk of it. The energy levels are divided into different like sub-levels and whatnot. The first thing we have to talk about are principal energy levels, which we colloquially call shells, like electron shells, okay? So we're going to call these, for now, principal energy levels, and then we can also just call them shells, like electron shells. And so we use a lowercase n to represent this. And so I'm going to say lowercase n can equal, and it's just like shell 1, shell 2, shell 3. Like, again, if we have our nucleus and then we have electrons can be over here, or they could be over here, shell 1, shell 2, and so forth. Again, this is like the planets going around the sun model. It's nice to simplify things, but it does not reflect reality in the shape of it, okay? But nonetheless, we have n equals 1, 2, 3, 4, and so on, okay? Just integer values. And then the principal energy levels are actually subdivided into sub-energy levels or subshells. And these subshells, for this course, there's 4 different types. And so there's like different types of subshells that can hold different numbers of electrons. And each of these subshells have different shapes that the electrons orbit, or different shaped orbitals that the electrons exist in. So the 4 that we're going to focus on, the 4 subshells, are S, P, D, and F. And so if you can remember like a PDF file, just an S in front, S, PDF, okay? So let's write over here, subshells, and here's the 4 that we're going to talk about. Is the S, the P, the D, and the F. Now, there are more, but the elements that we have basically like discovered in their ground states, which means when they're not excited, like we didn't add energy to them, the electrons are just in their natural state. They don't exist in any sublevels that are higher than these. There are higher energy sublevels, but for this course, we're not really going to pay attention to them. Like after F, there's G, there's H, but like you have to take a larger element and add a bunch of energy to it to get the electrons way up into one of those sublevels in a higher shell. Let's just ignore that for the time being and stick to what you guys really need to know for general chemistry. So these subshells are kind of like they're types of arrangements where the electrons can exist. And so what I like to do is make an analogy that if we have an apartment building, the principal energy levels, or like the shells, are like the floors in this apartment building. So, floor 1, floor 2, floor 3, floor 4, whatever. And then the subshells are like apartment types. like a 1-bedroom apartment, you know, whatever, like a 3-bedroom apartment. And so before I get to that, I'm going to introduce the next thing, which are orbitals. Orbitals are where the electrons actually exist. And these are the things that have a particular shape, like a particular orbital in a particular subshell, in a particular energy level, has a shape and a size, and we can have a mathematical equation that defines that, okay? So an orbital is a space that holds up to 2 electrons, okay? So I'm going to make a little chart here for the subshells and how many orbitals they contain, and then what the max number of electrons that each subshell can contain is, okay? So we have SPDF as the subshells. And by the way, this is all going to make sense in just like a minute or two, so just bear with me. So we have SPDF subshells, and then the number of orbitals is just the first few odd numbers. So if you can just remember S and then PDF, like a PDF file, like I said, the orbital numbers for corresponding to them are just the first few odd numbers, 1, 3, 5, and 7. Okay, so it's pretty easy. 1, 3, 5, and 7. And then an orbital can hold up to 2 electrons. So I'm just going to write max number of electrons, and then you just double the number of the orbitals. So if it has 1 orbital, an orbital can hold up to 2 electrons. So there's a max of 2 electrons in an S subshell. A P has 3 orbitals, so it's going to be 6. The D has 5 orbitals, so that'll be a 10 maximum electron count. And the F can hold up to 14 electrons. So now to continue on with my analogy here, if the principal energy level is the floor, the subshell is the type of apartment. So in other words, if I just say S subshell S, I didn't tell you what floor I'm on. I just said the type of apartment that it is. The number of orbitals is how many bedrooms, in my analogy, these subshells have. So the S type of apartment has 1 orbital, and it's like 1 bedroom. And let's just say you can have up to 2 people in a bedroom. So the max number of occupants in the S type of subshell is 2, because it's a 1 bedroom, right, 1 orbital, and it can have up to 2 electrons per orbital. The P is like a 3-bedroom apartment, so that's a maximum of 6 occupants, 6 electrons. The D has 5 orbitals, so it's 10 electrons. The F is 7 orbitals, so it's 14 electrons, okay? But that doesn't tell you what energy level that they're in. So now, let's figure out or talk through which floors, which principal energy levels have which sublevels, okay? It's pretty simple. Up until a certain point, each principal energy level or each shell number has that many subshells. And we always start at S from the beginning. In other words, shell 1 has 1 subshell, an S. Shell 2 has 2 subshells, an S and a P. Shell 3 has, guess how many? 3 subshells, an S, a P, and a D. And shell 4 has 4, an S, a P, a D, and an F. Now we have more shells. There's, shell 5, 6, 7, but they're really, we don't need to add more sublevels to account for the number of electrons in an element. So after we get to the F, we kind of just stop. So in other words, shell 1 has 1 subshell, 2 has 2, 3 has 3, 4 has 4, but 5, 6, and 7, they can have more for sure. But for the regular elements in the ground state, we're not going to have to go past the F, okay? So now, let's tie this all into quantum numbers, okay? So as I mentioned, the principal energy level, which we call the shell, we represent that with an N. And if we're tying this to quantum numbers, we call that the principal quantum number. And there's really nothing new here, just N equals 1, 2, 3, 4, 5, 6, 7, whatever it is. That's the number that N is. That's the principal quantum number. And so that's our first quantum number, okay? Is the principal one, it's the same as the principal energy level or the shell number. really nothing new here. And let's just fill this in a little bit to 1, 2, 3, 4, and 5. The 5's a little sloppy, but I think you guys get the idea. Now, the next thing was the sub-energy levels, which I call subshells. And so that's the SP, D, and F, right? Now, when we talk about quantum numbers, we refer to them as the angular momentum quantum numbers. It sounds fancy. You don't really have to worry about what that means too much as far as most general chemistry courses, but just know that that number corresponds to the subshell. And we use a lowercase l to represent that. And so if we take the subshells that I already taught you, which are S, P, D, and F, the number that we correspond to them, we just start at S and we give that a 0, and then we just count up. So S is L equals to 0, P is L equals to 1, 2, and 3 for D and F, okay? Don't worry about the value of the number too much. It's just correlating a particular thing, a subshell, to a number, so that at the end of this, we're going to be able to give like an address of an electron with just a series of numbers. So instead of having to say SPD, we're just going to say 0, 1, 2, and so forth, okay? And remember, if there are higher sublevels, like G and H, that would just be 4 and 5, whatever. So now let's go over to the orbitals. So as I mentioned, the S sublevel has 1 orbital. The P has 3 orbitals, the D has 5, and the F has 7. 1, 3, 5, 7, the first few odd numbers, is the number of orbitals that each sublevel has, okay? Now over here, we want to number them. So again, at the end of the day, I'm not going to say like the 3rd orbital in the, the P sublevel. We're just going to have a number for it. And so we use this variable m sub l, this L is a subscript here, and they range from -L to 0 up to +L. And so for S, -0 is just 0, 0, 0, and what so forth. So the m sub L value can only be equal to 0 for an S sublevel because there's only 1 orbital. And we're just like labeling that orbital as 0. That's like its name for this purpose, okay? The P has 3 orbitals. And like I said, m sub L, the values can be from -L to L. So they could be -1, 0, and 1. And that's 3 values, right? So we're just giving the orbitals in the P subshell just numerical values. So then if D has 5 orbitals, well, then we're going to expect that there should be 5 values for m sub L for a D. And if we just follow this little formula here, or this, algorithm, whatever, we go from -2 to -1 to 0 to 1 to 2. That's 1, 2, 3, 4, 5 orbitals. Again, these are just really labels, okay? And then, of course, if we get to F, it's just going to be from -L to L again. So L being 3 for F, we go -3, -2, -1, 0, 1, 2, 3, and lo and behold, that is 7 values, okay? And so that corresponds to the 7 orbitals in an F subshell. Now, the final thing is the spin. And I didn't mention this yet, but electrons have what we call a spin associated with them. And the idea is that it's kind of like, an analogy would be how a magnet has like a north and a south end. So electrons have a magnetic field associated with them. And so the idea was that a spinning electric charge generates a magnetic field. And if you spin one way, you make like a magnetic field going one way. And if you spin the other way, it goes the other way. It's a little more complicated than that, I suppose. It's a quantum intrinsic characteristic of the electrons that we really don't have to get into. But the point is, electrons have what we call a spin state. And we say they either have an upspin or a downspin. And we assign those a value because, again, we want to give a numerical address to every electron in an element, in an atom. And so instead of saying up or down, we're just going to call that positive 1/2 or negative 1/2. So m sub s can have a positive 1/2 or a negative 1/2 value. Those are the only values that I can have. So let's just write negative 1/2 or positive 1/2, okay? And so with these quantum numbers, that's them, n, l, m sub l, and m sub s, which is the principal quantum number, which corresponds to the shell, or the principal energy level, L, which is called the angular momentum quantum number, which corresponds to the subshells, or the sub-energy levels, m sub l is the magnetic quantum number, which corresponds to the orbitals within those subshells, and then m sub s corresponds to the electron spin quantum number, okay? And that's what we just call spin. Upspin and downspin, that's upspin, that's downspin, okay? So if we continue on with my analogy of the apartment building, let's just say for some reason, people, if you have 2 people in a room, they're going to sleep head to toe. Let's just say each room has 1 bed and you're going to sleep head to toe. And so that's kind of like the spin state, okay? Let's say that there's some rule in this universe of my analogy that 2 people can't sleep in the same bed head to head, okay? You have to, if you're sharing the same bed, you have to sleep head to toe. And so that kind of gives us the spin state. So in other words, we can say, what floor are we on? What's the principal energy level? What's the shell number? What's the principal quantum number? That's just n, 1 through whatever. Then the angular momentum quantum number is like the apartment type, right? So that's the subshell S, P, D, and F, which we give the numbers 0, 1, 2, or 3, or it could actually be higher, 4, 5, whatever. And then the m sub l, or the magnetic quantum number, is which bedroom are you in? Are you in, the first, second, or third bedroom? But we're going to call them like bedroom -1, bedroom 0, bedroom 1. And then the magnetic spin number here, or the spin quantum number rather, is just saying, are you sleeping with your head towards the headboard or your feet towards the headboard, right? That's spin up and a down spin. So something else to mention here is I gave you the values that m sub s could be. M sub l can be negative L to L. L is always going to be n minus 1 or lower. So it's going to be like n minus 1 to whatever it takes to get down to 0. So if we're in shell 1, like I said, shell 1 has 1 subshell, that's an S, which is L equals 0. And so 0 is n minus 1 in this case. 1 minus 1 is 0. That's the only value that you can have is an S, which is 0. Shell 2 can have 2 subshells. So we can go from n minus 1, 2 minus 1 is 1, there is a P, or down to 0. You can have a P and an S. 3 starts at n minus 1, which is going to be 2, which is a D, and then it goes down to the S, 2, 1, and 0, and so forth, okay? So those are all the values that we're allowed to have. The last thing is, if we look at a particular principal energy level, like let's just say shell 3, we can count how many electrons are the max that it can hold. Because we can look and we can say, okay, shell 3 can have 3 subshells, S, P, D. And S can hold a max of 2 electrons because, remember, it's 1, 3, 5, 7 orbitals. So an S has a max of 2 electrons, a P has max of 6, a D has max of 10. That adds up to 18. So that's the max number of electrons in shell 3. But there's also a formula for this, because if you get to higher energy levels, you may just want to use the actual formula. And that is, and let's just put this, let's just write this, I don't know, over here. This is good enough, right? 2n squared is the maximum number of electrons in a particular principal energy level. And so we can come up with the exact same numbers that I just gave you guys. Let's say shell 1. 1 squared is 1 times 2 is 2. That's the S. Let's say shell 2. 2 squared is 4 times 2 is 8. Well, an S and a P, 2 electrons 6 electrons, that adds up to 8. If we go 3 squared is 9, times 2 is 18. Well, we take the 8 that we just had, plus another 10 from the D, that's 18. And then if we add in, if we do shell 4 squared is 16, times 2 is 32. Remember that the F holds 14, so if we add that to the previous 18, we get the 32, okay, guys? So that's probably the last thing I really need to mention for this particular topic, but this leads into doing electron configurations and orbital diagrams. So I wanted to show you guys real quick what these orbitals look like. So if we look at the subshells, S, P, D, and F, we have L is equal to 0, 1, 2, and 3. Just remember, this is just a numerical correlation to what the subshells are. And now the subshell S type only has one orbital, so the orbital is just the S, right? Subshell, it just is an orbital. But the P has 3 orbitals. So we separate that into the PX, Y, and Z. Like in Cartesian coordinates, there's an X-axis, a Y-axis, and a Z-axis. It's kind of like left, right, up, down, and in and out, right? And that corresponds to the M sub L being -1, 0, and 1. Now the D gets a little wilder here, gets a little crazier, because now, and if you haven't gotten too far in math, this may look very exotic to you, but we have D sub XY, YZ, XZ, X squared minus Y squared, and Z squared, which corresponds to the M sub L values, -2 all the way up to 2. And F gets even wilder. But I wanted you guys to see what these orbitals look like, just have some context, because they're very interesting. And if you go further in chemistry, you're going to learn more about this stuff, like in PChem, like quantum mechanics and whatnot. All right, guys? So guys, if this helped, please give a like, follow, share, save this so you can review again later. And if you would like to go above and beyond and really support me, check me out over here, and you can patronize me. It helps me to continue making these videos for free. Thanks again, guys, and I'll see you in the next one.